We will continue with two more properties of the cross product, quite important and useful ones. The first one is the theorem which says that the length of the cross product of two vectors is the norm of A, the norm of B, and sine of alpha, where alpha is the smaller angle hence it's between 0 and pi, so sine is positive, okay, between A and B. Okay. Now, from here, we have a direct consequence, which I will state and write in a few minutes. It says that because we have sine alpha here, sine alpha is 0, means alpha is 0 or pi. So the two vectors are parallel in this case. So the cross product is 0 if and only if the two vectors are parallel. This will be a consequence which will follow in a minute. Let us first look at the proof of it. Okay, in the proof, let us start with the following observations. Observe that A cross B squared, that is A squared, B squared, minus A dot product B squared. Now, of course, it is not immediate, but one can check it quite easily. Okay. I would advise that you try R2 case. That would be easier, but the R3 case is also not very difficult. Okay, but then the proof is direct. That is to say, A cross B squared would be A squared, B squared, minus, now we know that A dot B is length of A, length of B, and cosine of alpha, where alpha is the angle between the two vectors. But we have a square, so we have square here, which means, of course, that we have A square, norm B square, 1 minus cosine square of alpha, that is sine alpha squared, but sine alpha is positive. Okay. We get the result. Now, the first consequence that we get from here is the following. Sine alpha is 0 means alpha is 0 or alpha is pi. So, okay, A cross B is 0 means, okay, A and B are parallel, because the angle between them is 0 or pi. So we get this nice consequence directly from the theorem. Now a remark about the direction of the vector. Okay. Well, we have a direction because we have a vector at the end. Where does it point? Okay. Now the direction of the vector A cross B obeys the right-hand rule. Okay. Namely, if you have a vector A and if you have a vector B, okay, well, their angle is something, then the cross product vector will be perpendicular to both A and B. So it will be something like this. Or it will point downwards. So the question is, which one? Well, we know that this is perpendicular to B, and it is perpendicular to A. Okay. So the picture will look like this. Well, it obeys the right-hand rule. So okay, it says again that we have the A vector, the B vector. So if you turn your forefingers from A towards B, your thumb shows the A cross B direction. Okay. Now, we will not prove this directly, but, okay, observe this in the cases, okay, I cross J is K, and so on. Clearly, I cross J is K means exactly that the right-hand rule is obeyed. Okay. So much about the direction as well. Now, two geometric applications. Well, the first one is about the parallelogram. That's to say, consider in R2, okay, consider two vectors, A and say B vectors, and form the parallelogram, okay, where the sides are parallel and so on. Then, okay, if you look at the area of this parallelogram, you need the base length and the height. This is your height. Then, of course, because if you take this triangle, which is congruent to this one, put it over there, it looks like the area of a rectangle. So area of the parallelogram is then the base length times h. Okay. But what is h if this angle is alpha? Okay. Clearly, h divided by b is the sine of alpha. So this is length of A times, okay, B times sine alpha, which of course means the length of A cross. So a geometric meaning in plane of the length of the cross product is precisely the area of the parallelogram determined by the two vectors, A and B. Okay. Now in A3, in R3, we can generalize this slightly. Okay, that's to say, take two vectors, A and B. Now to these, add a third vector, C. That is not add, of course, but put another vector. And, just shift all sides with this vector. Okay. Well, what happened? This should be somewhere here like this. So it looks like a box determined by the three vectors. Okay. Actually, these are all parallel. It's parallel to C, and so on. Well, it's not, of course, a box like a rectangular box, because you have three vectors and you don't know anything about the angles between them. It is called a parallelopiped. Okay, it is just three vectors, shifted to form a certain volume. Okay. Now, this here, everything is parallel to everything. So, the volume of the parallelopiped is its area times height. Okay. The area we know. It is A cross B. Now the height, is this one. Okay. You multiply the base with the vertical height. Of course, it's perpendicular to the xy plane and so on. And so, we get this height. But now, look at this angle, alpha. Okay. Now, alpha is the angle between the z-axis, in this picture at least. I will comment on that as well. And C. Okay, the vector C. So the height h becomes C times sine alpha. Oh, sorry, cosine alpha. Cosine alpha. Okay. But then, we have the following. We have the length of a vector, and of course, A cross B has the direction as the H line here, because if we think of A and B in the plane, the cross product will be perpendicular to that. So it will be in the K direction. Or if not, this does not change, because you can just move this box-like thing and put it in the xy plane, so that this point is the 0 point, volume will not change by translation or rotation. So then, okay, this becomes A cross B, the vector, length of the vector, length of the other vector, but we have cosine alpha, and it is this, the dot product. Of course, you cannot put parentheses anywhere else, but let me emphasize it. This is because, okay, A cross B is in the same direction as H. So, okay, this is nothing but this dot product. Now, in the figure, of course, we assumed a lot of things in a nice way. That is, the dot products are positive and everything is nice because of the configuration. Normally, the directions do not match. So in general, the directions do not match, and this can be negative. So, okay, put absolute value. Namely, okay, let me use the correct chalk color. Namely, that put absolute value here, so that you get the volume of the parallel piped. Okay, now let us. Okay, we did not have any exercises about the cross product yet, but within these applications, we will have it now. The first task is to find the area of the triangle with vertices at P1. This is a planar triangle in a plane, 1, 0. P2 will be at 2, 1, and P3 will be at 3, 3. Okay, the points are not important. Now we have 3 points in the plane, which of course determines a triangle within. But if we extend the sides, we will get a parallelogram. Namely, okay, in plane, we have, okay, say 3 points, P1, P2, P3. This is not exactly these numbers, just to explain things. Okay, and we have a certain triangle. Okay, but if we consider the vectors, okay, here and here, okay. Sorry, that would be wrong. Just this one and this one. So we consider these 2 vectors. Okay, and extend them. Okay, then the cross product of these 2 vectors would give us the area of this parallelogram. That's what we said a minute ago. So, okay, the P2, P1 cross P2, P3 is the area of the parallelogram. Determined by these 2 vectors. But from elementary geometry, because of parallelity of these sides, the two areas of these triangles are the same. Okay? And area of the triangle P1, P2, P3 will be 1/2, okay, P2, P1 cross P2, P3. Its area is half the area of the parallelogram. So all we have to do is calculate this cross product. So what is P2, P1? That's P1 minus P2. So P1 minus P2 is, of course, 1 minus 2. That's minus 1 and minus 1. And P2, P3 is P3 minus P2, and that is 1 and 2. Okay. Now we want to calculate their cross product, so we extend them by zeros. So then, okay, the cross product of P2, P1 with P2, P3 means the determinant of I, J, K. Now the first vector P2, P1 is minus 1, but we extend it with 0. Because we have to have it in R3. The second one is 1, 2, and 0. So we have this. Okay, of course, I have my ijk's here, and I have my minus 1, 0 here. And so, if I look at my diagonals, this would be 0. Okay, this would be minus 2k. Okay, and the last one will be 0. Actually, 0 vectors, because 0 times a vector, and minus, okay, this is minus k, okay, this one. The other ones are zeros, and hence it is minus 2k plus k, so it is minus k. Okay. Thus, okay, the area of P1, P2, P3, the triangle, okay, would be 1/2 of the length of minus k. So it is 1/2. Okay. So this shows how we can extend to R3 and do the calculations there. Now the cross product will be much more useful in the coming discussions